Check. What is up? Let's see. Let me make sure the beat is working. There we go. It should be working. Okay, I'm just going to continue with more distortion algorithms. So we have a soft clip so far. Also, I don't know if I've ever showed this, but I own Plugin Doctor, which is really handy. So let me show you. So you can load in a plugin. So let's get the one that we're working on right now, which is oversampling. Yeah, oversampling demo. So here's our plugin, and then it'll show you a couple of different things. So here's like a frequency analysis, a real simple one. You have performance. You can check out dynamics. There's an oscilloscope. So if we turn the drive up, we should see, yeah, we get the soft clipping. You can see the soft clip as compared to no soft clipping. There's a Hammerstein, which I don't really use. The harmonic analysis is really handy because it kind of shows, I'm going to pull up some of the gain, and then if I turn on the oversampling, you should see some more high frequencies come up. Yeah, so this is a good way to make sure that your oversampling is actually working. And then another thing, we could check the performance of the oversampling, so we can see that it's running pretty quick. This is our buffer size, and you can see how fast it's running. And if we turn oversampling on, it gets way slower. So it's using more CPU and it's taking longer to calculate things. So that's pretty handy. And then we have linear analysis, which is pretty simple. It's not going to really show us too much for this, but if we had a filter, it would show us the curve of the filter, which is pretty handy. I use a lot whenever I'm like modeling, you know, like a pedal or something like that. You can also, instead of looking at the frequency, you can look at the phase response. And since it's distortion, there's really no phase. There's really no issue with phase. And then if we turn the oversampling on, you can see there's some phase issues at the very top. But this looks crazy, but it's really not that bad because you can see that. So like if we just start from like right here, we're going up and then it wraps back down, and then it goes up and then it wraps back down, and then, you know, it's fine over here. So like something like up until like this point right here maybe is like fine. That's not really that big of a deal. And then this is where it kind of like gets bad, but you know, it's whatever. You can also look at, you can see what happens with white noise. So a lot of really cool stuff that you can do with this plugin. I use it a lot. I think it's either like $30 or $40, so it's not too expensive. And it's very accurate. People use it in the industry, so it's really good. So we have a soft clip. So let's do a hard clip. So what's a hard clip gonna do? Basically, it's just gonna only prevent amplitude values above like 1 and -1, right? So it's gonna clamp your signal down if it goes out of the range of -1 to 1, which is a really simple, you know, it's just an if check. So the soft clip, you could see that it was kind of rounded. Let me pull it back up. So let's go to the oscilloscope, and then if we pull the soft clip up, you can see that it gets really rounded around the edges. Now the hard clip is going to make it look like a square. So basically it's going to take anything that goes above the threshold, which, you know, usually is -1 to 1, and it'll just move it down and assign it to whatever that threshold value is. So that's what makes it look like a square. So let's just implement it and then we can look at it. So we're going to do something similar. We're going to say float we'll say hard clip data. And I'm going to take this hard clip data. Very nice. So basically all we have to do is, if the input goes above 1 or -1, we just need to wrap it back down. So let's start by, let's see, if, now we need 1 or -1, so we could check that by just using the absolute function. So if the absolute value of sample is greater than 1, meaning that this will equate to true if it's -1 or 1, because we're using the absolute value. And then, so if it is, we're gonna say samples is equal to, and we could say is equal to 1, but that means that if it goes above -1, we're gonna assign it to 1, which wouldn't be correct. So what I usually do is I'll say samples times equals 1 divided by absolute value of samples. So in this way, what we're doing is, if it goes above 1, we're multiplying the amount going over by, let's see, wait, no, that's not correct. So we're taking the samples and we're multiplying it by whatever we would need to map it back to under. So hold up, let me just pull up the calculator and show you. So like, if our value is 1.5, right? So that would be samples. So let's say times equals, so times 1.0 divided by 1.5. Right, and then we get 1, right? So this is letting us just use one expression to kind of handle whether it's negative or positive. So anytime it goes above, we're multiplying it by 1 divided by the amount over, or the total over, and it's mapping it back to the right value. So even if this was -1.5, it would work the same. So that's why this mathematical expression works, because instead of having to check for both cases if it's above 1 or above -1, you know, we don't have to do that. We can just use this expression. And then let's see, we just return the samples. And that should be it. Very simple. Let's check that. And then we're also going to make a way to switch between the different distortion types we have. So let's build that. And we'll check it and plug in Doctor. Okay, cool. So one thing we noticed is that we don't have a volume drop anymore where we had it with the soft clipper. So we could probably fix that with the soft clipper, but it looks like the hard clip is probably gonna work. Okay, so we've got that. If we pull it up, oh, wait, oh, because I gotta, okay. Let's see here. I forgot to put. I assumed that the drive was happening up here, but it's not. So let's do hard clip data, and then let's put it. Well, actually, we'll just put it in here. So let's just do samples times equals raw drive or raw input. That should do it. Okay, so there we go. Here's the oscilloscope. There we go. You can see how it's squaring it now. It's not really soft anymore. The soft clipper was rounding out the edges, but the hard clipper it's just basically a square, right? So all it's doing is if it goes above 1 or less than -1, it's just mapping it back down to that range. So that's pretty cool. That's hard clipping. Doesn't get more simple than that, but there's actually a bunch more that we could do. So we could do half wave rectification. So let me make a method and we can talk about that. Let's see. Half wave data, sure, whatever. Half wave data. Okay, so what is half wave rectification? Basically, all it is taking all of the negative values in the signal and assigning them to 0. So let's do that and see what it looks like, because it'll be way easier to explain it once it's there and we can look at it on the graph. So we're going to take all of the samples, and if they are less than 0, we are going to set them equal to 0. Okay, so take the same thing. Let's do samples raw input, and in fact I want them all to look the same, so let's take this and do that just so that they're consistent. Okay, and then we're gonna say if samples is less than 0, so if it's negative, samples equal to 0, and then we need to return it. Yep, that should be good. And then we will actually call the half wave data. Let's see what that looks like. We shouldn't have any volume drop. So let's see how it actually turns out. Where are you at? Oversampling. Okay. Okay, cool. No volume drop. Let's check out the oscilloscope. There we go. See? All of the values are now, if they were negative, they now equal 0, which is kind of it's almost like a hard clipper, but for just half the wave. So let's see. We could probably have 2 versions. Let's do it with one where instead of hard clipping it like that, let's do the soft clipper inside of here. So let's do this. If samples less than 0, samples is equal to soft clip data samples. Let's see if that changes it. My hope is that it'll round off the edges. So yeah, let's see if that did anything. I don't know if it'll do anything, because that wasn't something I tried. I just thought of it just now. Oversampling. Okay. Oh yeah, look at that. It is rounding it off. I wonder what would happen if there's so many combinations that we could do. So like so we're soft clipping it, but we can also soft clip the entire thing. There's so many options, because if we start mixing, matching everything, like there could be like 15 or 20 different combinations. And then it becomes, how do you make a GUI to handle that but makes sense? Let's go to oscilloscope. Okay, interesting. Okay. Let's do hard clip data instead. That way the positive part of the wave will have the same amplitude, hopefully. Okay, yeah, so top part of the wave still has the right amplitude, but the top is now hard clipped and the bottom is oh, okay, but when we get too much gain, the bottom is also hard clipped. So it would be cool. This isn't really what I expected. I kind of expected the bottom to soft clip like we were seeing. So maybe does it make a difference if I just call hard clip after? I don't know if this will make a difference, but let's see. No, it didn't make a difference. What if I'm really trying to get the bottom to like be soft while the top is hard clipped? Which we could do with an if statement, but I just wanted to see if there was a kind of intelligent way we could do this, because okay, so we don't have the hard clipping anymore, so let's take a look at what that looks like again, and maybe I can better explain. So this one right here, okay, and oscilloscope. Okay, so this is just the regular half wave rectification with, instead of setting equal to 0, we're soft clipping the negative part. So you see how it looks like a soft clip right here, but then the top part of the wave is increasing. That's what I want. Yeah, I'm gonna have to do with the if statement because I want the top to be hard clipped, but I want the bottom, or I want the positive part hard clipped, the negative part soft clipped. And I don't think there's really a way to do that without an extra if check. So like if that, definitely don't want to do that. So samples is equal to hard clip data samples. So let's do what we want. I was hoping there was a way to do it without, you know, another check, but I mean, it doesn't matter. Okay, let's check it out. There we go. Interesting. This kind of resembles tube distortion. Let's see if I can find an example. Tube distortion. Oscilloscope. Yeah, this is what I kind of expected. This is kind of what I think about. This is like the more common look. That's what tube distortion usually looks like. It says Telecaster guitar, but that's just the form. So cutoff and saturation shown on an oscilloscope. I wish it would have more than that. So this is apparently fuzz. There's actually a lot of cool stuff on here. But yeah, this is the basic tube distortion look. So let's see what it sounds like. Did I have a project made for this? Yeah, sure. The stream intro. Okay, waveform view. Oh yeah, I need to release that video. I need to edit all that together. So here's our drum sample. Let's check out your DSP. What am I looking for? This one. Okay. Okay. So the one thing that I notice is that there's that weird rattle that I get from time to time with distortion algorithms. So I'm going to try a couple of filtering things to see if it fixes it. But one thing I know we could do to fix it is to add a bias. So let's just see if maybe like a DC offset filter would do it. So just a high pass. No. Yeah, because it's in here somewhere. So let's try a bias. So one way we could do that is we could add a value in at the beginning and then subtract it out at the end. So usually a good value that works, it seems to work all the time, is 0.25. And we subtracted out 0.25. I think that's how it works. Didn't quite do it. I'm using the right one, right? Yeah, okay, half wave. Okay, let's do this. I don't know if it'll make a difference, but okay, let's try like that. So it works until a point, and then it kind of gets weird. Well, I guess I could try this. Let's put that first. Oh, okay, well, I got more out of it. It looks like I can get up to 9 dB of input gain before it gets weird. I wonder what happens if I, you know what, before I keep doing that, instead of hard coding that, let's make a slider that does this for us. So let's do another one of these. I'm gonna call it bias. And this is gonna be from 0 to 1. It's gonna start at 0. Okay. We're gonna add it to the parameter vector so that it actually gets put up there on the screen. I need to make sure that we put our listener. Okay, we need to make a variable in the header called bias. So let's do float bias 0. Okay. Now, and we also want to make sure that when the bias moves that we're actually setting that variable. So let's go into our parameter changed method, add one in for bias. And we'll say bias is equal to new value. And if you remember, new value is the value that's coming in from the listener. Okay. And now we just need to go into here. And instead of that, we'll do bias. And bias. Okay. All right, that should be good enough, I think. Okay, let's check it out. That works pretty good. Okay, so at least we found that a bias of 0.1 works pretty well. Let's try some other sound sources. Or actually, let's take a look at what that looks like in the oscilloscope. So it looks like I'm gonna put 0.1 so that I remember. Okay, let's check it out on the oscilloscope and plug in Doctor. Okay. Okay, so yeah, it just looks like it's shifting it, but interesting. Ah, but because of that, yeah, because of that, the negative part of the wave is actually going out of the bounds. So let's see. How could we address that? If samples. Maybe I should do this. Maybe that. Okay, oscilloscope. You know what? This is the negative part of the wave, so I should probably be adding it in. And then maybe I'd subtract it out at the beginning? I don't know. Oscilloscope. That. In. Okay, well. Okay, so that's with it in. Okay. Now, what does it look like if I don't actually... Oh, no, I need that. Okay. So let's see what it sounds like. If it still sounds good. Nope, sounding weird. Yeah. Plus minus bias. Oh, and then you know what we could do? So we'll say samples minus equals bias, and then we'll return soft clip data samples. Let's see what that does. Okay. That's something. But it looks like I don't really need 24 dB. It looks like 10 dB is good enough. The only weird thing is that the volume needs to be multiplied by 2, but if you multiply the volume by 2, it'll be out of range right here, and it'll be like immediately hard clip. But let's just see what it sounds like. And we've really gotten away from a regular half wave rectification. Sounds good. So you know what I'm gonna do? I'm gonna rename this and make another one. Or actually, I'll just make another one. Cheap tube. Cheap tube. And I'm gonna switch this to 0.1 since I know what it is. And then if we need to use the bias somewhere else, we can still use it. So we'll call this cheap tube. And I'll go back to half wave. And we'll say samples plus equals raw input. And if samples are samples times equals 1.0. Oh wait, no, halfway rectification, 0. And then return samples. Is that what we did? Halfway data. Okay, it is already using halfway data. Okay, cool. Let's build that and make sure it's doing what it's supposed to do. Yep, okay, there we go. It's clipped to 0. And there's no bias. Okay, so that's half wave. So let's do full wave. Full wave data. And we're gonna make it right here. Full wave data. Okay, so same thing. We're going to take samples and we're going to get our input scaling there. And full wave is going to take all of the negative values and map them to their corresponding positive value. So we can basically take the same thing here. And if the values are negative, instead of saying samples equal to 0, we could say samples. We could either say samples are equal to the absolute value of samples, or samples times equals -1. And multiplying it by -1 is going to be way less CPU intensive than using the STD absolute function, which it's not like it's going to use a lot of CPU, but you know, using multiplication is faster. So any little bit of optimization you can do will help out in the end. So let's do times equals -1. And that's pretty much it. Full wave and half wave. There we go, it built. Okay, it's loaded in. And yep, there we go. Everything that was negative. So, you know, here's the top part of the wave. So anything below it would be negative, meaning that this should be empty space right here, but it's not because it got mapped to positive values. So that's right. So that's another thing. There's all kinds of, like, the options are like endless, because we could hard clip the negative part. We could hard clip the positive part. There's just so many things that we could do. But let's keep going. Okay, so we have a soft clip, a hard clip. We've got our cheap tube, half wave, and full wave. So let's make a way to switch between them. So we're gonna make a choice parameter, but we need a list of choices. So we use a juice string array. And let's just say distortion models, and we've got soft, hard, tube, half wave, and full wave. Perfect. Okay, so now we need to make a choice parameter, which is in the generic audio processor is going to give us a drop down menu. So let's take it doesn't really matter. Let's take I guess, yeah, we'll put it before input. We're gonna say models. And instead of audio parameter bool, it's gonna be audio parameter choice. Okay. And then this is gonna say model. And it's gonna take in the string array. And I think it takes in how many things there are, so, and then which one you want to start on. I think, are there 4? Is that what we did? 1, 2, 3, 4, 5. Okay, there's 5. Okay, so let's put it in the vector. Okay, let's add a listener. Here, okay. We're also gonna need to do something whenever it gets, whenever the value changes. Okay, model, which for now will be nothing. So we have 5 different things that we're going to choose from with the choice parameter, and it's going to give us an int. And the cool thing about ints is that you can use them for switch statements. So we could either create an enum out of them or just use the ints, but using an enum will be more significant to us. It'll make more sense. So let's make an enum. So let's do an enum class. Let's do it like this. Enum class, distortion models. K soft. K hard. K tube. K half wave, and then K full wave. Okay, that, and then we can also set which one it starts out as. So we can say dis models, dis model, which will be our actual variable, and we can set it equal to one of them. So dis models, come on. So we can start it at, I guess soft will be first. So soft. Okay. Perfect. Okay. And then what we'll do is in here, we'll say if actually we could do a switch. So let's do a switch and let's see. Let's make sure we're getting an int from it. So we're taking in new value, which will be 0 to 4, but it's actually coming in as float, so we need to cast it to int so we can use it with the switch statement. And we'll say case 0. And let me get this out of the way. We'll say this model is equal to this model soft. Okay. And that's it. We just have to do the same thing for the other choices. So case 0, 1, 2, 3, 4. 1, 2, 3, 4. And it's a good idea to just go ahead and use the same order that you did in the string array. So tube half and full. Okay. Oh yeah. Semicolons right here. Okay, that should be good. And then we should be able to we could debug just to make sure that we're getting what we think we're getting. This model, not 100% sure. Will it give us the integer? Probably. Interesting. Let's see what std gives us. std cout. This model. And then just do that. That should work. Huh? Oh, it's still. Okay, well, let's do this. How about that? That should work, right? Okay, cool. So let's just do it in standalone and see what we get. Oh, we got a build failure. No matching initialization for choice parameter. Very cool. Let's see, model. Let's just go to documentation and see what it wants. So it's audio parameter choice. So the ID, the name, the oh, okay. So just the default item index. Okay, soft. That should be 1, and then 2, 3, 4, and 0 up here. Yep. Okay, so that's working. Cool. So we can take the debug out, unless something breaks in the future. And then what we could do is call a or do a switch statement in here. So switch on this model. We'll say case soft. Soft clip data. Okay, let me take this out, and then I'm sure you can guess the procedure for the rest of them. Okay. Hard, tube, and half wave. Yep, and full wave. Okay. So here we just got to say hard clip data, cheap tube, half wave, and full wave. Hope those names are correct. So that, and then we'll just do that also for this version right here. And that's probably it. Okay, let's see. Let's see if that worked. Let's pull up plugin doctor. Okay, oscilloscope. We've got, I don't know, it looks like half wave or something, right? Let's go to soft. Oh, hard. Tube. Something's not right. Half wave and full wave are right. Tube. Hard. Weird. Did I do something wrong? Oh, I didn't say break. I hope that's what it was. Because I'm assuming if you don't say break, it's just gonna do all of them. Okay, oscilloscope. Okay, there's the soft clip. Here's the hard clip. Go back to soft clip. Yep. Tube. Yep. Half wave. Yep. Cool. Okay, so that's working good. Now I will say that half wave and full wave, there's not really anything meaningful that input does to it, driving the input, which is why we probably want to, like, I don't know, I guess soft clip it. So we could say, let's see, in the half wave. Yeah, and then we could say soft clip data. And then I guess the same thing for full wave, soft clip it. Cool. Okay, so let's see here. Oh wait, why am I pulling up Logic? Let's pull up plugin doctor. It's thinking. It's taking its time too. Hey chat, check this out. I got me a mini fridge on my desk now. Dr. Pepper, if you're watching. What's up, Agent Victor? Are you Victor from the free VST page and the gent posting group? Oh, that's cool. So half wave and full wave. Yeah, so now they're a little more meaningful. They're actually distorting. Okay, cool. Oh, you are. What's up, man? Check this out. You want to see something beautiful? Besides that, something else that's beautiful. This right here. Well, good to have you in chat. I'm working on just making a bunch of distortion algorithms for different concepts in distortion. I've got soft clip, hard clip. I've got me this cheap tube distortion that I just kind of made up on the fly. Half wave rectification and a full wave rectifier. I want to see what the wave rectifier sound like. Well, I'll show you. Let's check out, let's see. So here's a drum loop. So that's soft clipping. Let's do a hard clip. Sometimes it's hard to tell the difference between the hard clip and the soft clip. But here's the tube. One thing you could probably do with the tube distortion is also add some filtering to make it a little darker and warmer sounding. Okay, I want to try the half wave and full wave and see what they sound like. Oh. Yeah, they need a bias. Yeah, they need a bias. Let's see. That's cool. Yeah, they need a bias. So let's try that. So, okay, so we could probably just go and say, okay, we could say samples minus equals bias. No, plus, right? Add it in first, then take it out. So should I do it here before the return? Let's see if that fixes it. I'm not sure what the purpose is. I'm sure it happens in guitar amps and I'm sure it happens in analog circuits for different components. So I'm not sure what the actual use case is supposed to be for it. I just know that it's a thing that exists. But yeah, not 100% sure. I'm sure some electrical components do it, especially in a DC circuit. Yeah, it actually makes sense because like an alternating wave in circuitry would look like a sine wave, and then when it gets converted to a DC signal, it should look like a sine wave with no negative part, and that's what half wave rectification is basically doing. And so I don't know, maybe it's to convert from alternating current to direct current. Yeah, I'll show you what they look like. Let's see what it sounds like. So it seems like any bias value fixes the half wave. So 0.15. that. Let's try it with the full wave also. But instead of hard coding, I'm gonna do bias again. We're not sure if that's gonna work well for the full wave, so let's build that. Okay, so I'll show you on the oscilloscope. So here we go. Okay, we got our oscilloscope. Okay, let's make sure everything else is working. Soft clip. Yep. Hard clip. Yep. Our cheap tube. Yep, sure looks like tube response, except when you go way too far. And then, okay, so here's half wave now. Right, and I've got soft clipping added to the half wave so that having an input variable would actually be meaningful. So now, instead of just having one setting, you can actually distort the positive part of the wave. And then here's what the full wave rectification looks like. This one's weird. This one I'm not sure what the use case is. I'm not sure if there's an electrical component that does this. I'm sure there is, but I don't know what it is. Yes, come see. Let's see if we can get it to sound good. Okay, so that's a half wave. Okay, cool. It's weird because adding in the bias fixes the weird artifacts for the full wave. Like right here. But you lose the weird, you lose like the lo-fi feel that it has naturally. So without a bias. Here there's like almost feels like there's a high pass filter on it, and there are like some weird stuff happening in like the mid-range. But if you add the bias in, you lose that. I guess it's not that bad. Yeah, it's not, I mean, you still get the idea of it. So let's do 0.1. 0.1. And the cool thing with the half wave and full wave rectification is you've got the signal split. So if you want to do anything weird, like we could add all kinds of options where, like, so half wave right now, all we're doing is if the samples are negative, we're setting them equal to 0. We're doing our bias, which we can kind of ignore. That doesn't really affect it. And then we're soft clipping the output of it. And what we could do is, instead of setting the negative samples to 0, we could do something else creative. And we could also only soft clip the positive part, or only soft clip the negative part, and then hard clip the output. There's so many options and mixing and, you know, mixing and matching that we could do to make it creative. So I'm not 100% sure. What else is there? We could add some filtering. Yeah, let's do that. Be the easiest way to do it. Do I have my modules pulled into this? Let's see. Yeah, let me pull in the. Or actually, no. I'll just use. I'll use the juice filters. I'll just use the like the LR filter. Yeah, let me do that. Okay, so in Juice's DSP module, Jesus, okay, we've got the Linkwitz-Riley filter, so let's do that. And I'm gonna do a low pass. So low pass filter. I need to come into the prepare method. Oh, I already have this set up. Okay, cool. So we'll say that, and we'll say low pass filter dot prepare. We'll prepare it with spec. Okay, and then I need to make a slider to actually allow us to change the cutoff. So let's do after input. Just copy that, and I'll put it after input, and I'll say cutoff. Okay, we'll call it cutoff. And this is gonna go, I don't even know. I guess we'll just do the full range. Yeah, in fact, I'm gonna just take, I'm gonna take something from another project. Where is it at? So yeah, we'll take this, I'll make it a normalizable range from 20 to 20,000 with the right logarithmic scaling, and then I'll just set it to, like, I don't know, 1,000 by default. Okay, we need to add it to this vector so that a little slider comes up. Cutoff. And then we need to add a listener so that something actually happens when we change the slider. Cutoff there. Let's make a cutoff variable in our header. Cool. Now we can go into our listener right here, and we'll say if it's cut off, we will make cutoff equal the new value. Yep, that seems right. We'll go to the prepare function. We'll make sure that the low pass filter is in fact a low pass filter. So set type, I assume it's in the same namespace. Linkwitz-Riley filter type, okay. And I'm doing a low pass. Okay. Let's also make sure that the cutoff is what the cutoff actually is. So we'll say tree state, and we'll load the cutoff. That should be good. And last thing we need to do is actually process. So we will say if oh, you know what's annoying? I don't feel like actually worrying about the filter for the oversampling logic, so I'm gonna only put it in the non-oversample part. So let's go here, okay, right there. So we'll say low pass filter dot process, and processing context, it's juice DSP process context replacing float and the audio block, which is called block. I think that's it. Okay, so let's build that and see if anything happens. Now, when you put a filter after distortion, it shapes the wave even more. If you put the filter before the distortion, it doesn't change the shape of the wave, but it does change the way it sounds, which is an interesting thing to experiment with. So let's go to plugin doctor. Yep, and we do have a low pass filter. We can see it there, and it's not changing. Oh, I'll tell you why it's not changing. Because we need to go into parameter changed and not just set cutoff to new value. We have to actually say low pass filter dot set cutoff frequency to cutoff. Why are you trying to sleep on the keyboard? Like that. That should work. Cool. Okay, so that's soft. Let's go to oscilloscope, and so we'll do that, and then we'll change this. Yeah, check that out. It changes the way the wave looks significantly, but it's also dependent on the frequency, so you can't really rely on, like, so we're at 20 hertz right now. Basically, I'm only using 20 hertz because it's easy to like actually see. I wish that plugin doctor automatically scaled whatever frequency you have to make it easy to see. Because like if we go to like at 288, we're already like, you can't really see what's going on unless there's something I'm unaware of. Kind of like Maxim SP has a scope object, and it has an automatic mode that no matter what frequency it's at, you can easily see the wave. Yeah. So I'm gonna go back to 20, and if we go to hard clip, we change the cutoff. I think it won't really do that much. Okay, actually no, that looks like a screamer. Oh, but the volume is before, so I'd have to implement a output volume so that we could see what's going on a little better. Here's the tube. So this is a setting that I want the tube to be at, something like that. And then if we do a little bit of filtering, yeah. But the thing is, see how we have to have it at the cutoff at 100 for it to look like it does anything? That's only because the frequency is 20. If the frequency was, you know, a guitar, we could set this cutoff to be, you know, like 2000 or 2500, and it should do what an overdrive pedal does. So, also, one thing I need to do, I've noticed that the tube model, the max it should go to is like 10 dB. So let's put that in there real quick. That's easy to do. We can just force it no matter what the plugin is set to. Whatever it's coming in is going to be yeah, okay, so we're going to say raw input is equal to jmap raw input. Oh, wait. This isn't dB, so... okay, this is what I'll do. Okay. I'll just see what the values are. Do I have a snippet already made for that? Let's see. Mix. Sharpless strong. Oh, I don't have one saved. That sucks. Okay. So, let's see. I'm just gonna make a quick dB to gain converter so I can see what the output values actually are. How $? No. 10 raised to the input divided by 20. And it goes to 24. So this would be dB and the bottom would be gain. Right, so okay. 24 is 15-ish. Okay. So we could probably just say raw input, which is from 1 to 16, to go from 1 to, what did I say 10 was the max? 3, sure, okay. These need Fs. Because JMap explicitly wants floats for some reason. All right, let's check it out in Logic. Or actually, before we go to Logic, I want to make sure that this Logic is working. So let's go to Plugin Doctor. And we should be able to see that on soft, we have the same amount of gain. On hard, we have the same amount of gain. On tube, what? What? Yeah, I bet it doesn't want the same variable. Okay, so let's do this. Let's do float new input is equal to overall input, blah, blah, blah. So we'll say this, and we'll just put new input here. And yeah, that's it. Let's see if that does it. I bet it didn't like that we're using the same variable for both sides. In certain situations that works, but in certain situations it doesn't. So it's just a weird C++ thing. So, tube, perfect. Well, actually, hold up. No, it's still too much. Why is it still from 1 to 16 and 1 to 3? That's new input. It's always this stuff that takes, like, designing the distortion didn't give me any problems, and then just trying to scale back the slider values is going to give me problems. dB input is equal to new value. Oh, you know what? I probably could use that dB input instead, so I could do new input is equal to dB input, and instead of 0 to 24, it'll be 0 to 10. And then we would say decibels to gain for this new input thing. Does that work? Bro. Why is this not working? Okay. I'm gonna brute force it. Okay, so what we're gonna do is What is 10 divided by 24? 0.4. Okay. So we're going to say right here. Okay. If this model is equal to this model tube, we're gonna take this, we're gonna say dB input times 0.4 else dB input like that, and then I should be able to not do anything special in the tube. Yeah, so raw input, come on, raw input, get rid of this, put my semicolon, and let's see. If this doesn't work, I'm gonna lose my mind. Okay, so take the cutoff, go to tube, go to oscilloscope. Okay, thank God. All right, so that works for the tube. And then if we go to hard or something else, we should have normal. Yep, that works. Okay. Oh, that's weird. I don't know why that's happening. Oh, maybe because of the cutoff? Interesting. Okay. Full wave, let's see. Huh. Well, I'm gonna ignore that for now. And let's go check out and see what it sounds like. What? Wait, what? Endless loop? What? What do you mean? I don't know what you mean. Oh yeah, it's an endless loop. There's a lot of the stream where I'll be like silent for a few minutes, so I figured having music in there would make sure that it wasn't awkward or too quiet or whatever. Is it bothering you? I can certainly lower it. Yeah, whenever I get monotone, the music helps. And what I'm supposed to do is whenever I go to Logic or something, I'm supposed to remember to turn it off. Like this. And I forget a lot. Let's go to the tube. Let's go to a project that has some guitar in. Where's it at? Plugin. Where's plugin tester? Right here. Okay. All right, man. Go get you some sleep. Hope you sleep well. Have a good night. I remember kindergarten. That was rough. Take this. Let's see. Wait, I'm gonna just check right here. Well, I have oversampling built in, so that should take care of aliasing. And I could go up to 16 times oversampling, but usually whenever I calculated it, nothing over 4 times oversampling was really necessary. But yeah, I could do oversampling up to like 16 times, which, you know, if you do 16 times, you're definitely not going to get any aliasing. So instead of that, let's go to oversampling demo. That sounds pretty good. I am not gonna lie, that sounds good. Oh, let's check it out from the beginning. Oh, here we go. Bro, that sounds good. Sounds really good. Wow. Pretty proud of myself. Okay, so didn't know this was gonna turn into a real plugin. Thought I was just making a demo video, but I might have something here with this this dumb quick tube prototype that I made. Basically all I did was try to make the shape of it match what a tube distortion is supposed to look like, and it's, I don't know, it seems to be good enough. And adding in the filtering helped a bit. Sounded pretty cool. Yeah. So I guess the only thing left to do really is to make sure that when oversampling is turned on, we need to make sure that the filter, the sampling rate, the filter changes internally. Because if you don't do that, the filter will break. So we can do that. I feel like there's definitely more creative opportunity in this distortion. I mean, we can do all kinds of stuff, especially with the half wave and full wave, because we're already splitting the polarity. So we've got a positive and negative part. So we could do something independent to each polarity and get pretty creative with that. But yeah, I think that's going to end it for me. I'll be back Wednesday. We can continue on this. But yeah, hope you enjoyed. I'll turn this into some clips, and thanks for watching. See ya.